So here is some practice with integrating factors. What do you do if it's not an exact equation, but it's super duper close? So previously we looked at a problem, and if you missed the video, you can probably find it. But previously we looked at the video here. We looked at this problem, and we tested it out, and we said, okay, so dy of 3x plus 2y squared, well, that was 4y. And dy, talking too much, ddx of 2xy, well, that was just equal to 2y, so it's not exact as is. So we had to use an integrating factor. Okay, so to come up with that integrating factor, what we did is we looked at my minus nx over n, and if it's only factors, if it only has x's, then use it. So we did 4y minus 2y over 2xy, and in fact we got 1 over x. Now there was also one for using y, so the other side of that was if nx minus my over m is only y's, use that. And if you don't know what I'm talking about, go find the video on that one, because you definitely want to see the theory behind this, because if you don't see the theory, it looks a little crazy. So basically we're going to use e to the negative 1 over x dx, which is e to the ln x, which is x. So that means we're going to multiply the entire original equation here by x. And whenever we do that, we will get, hold on, what was the original equation? I've already forgotten. I'll write it down here and then I'll move it around. Okay, here it is. So we're going to multiply this entire equation by x. And we're going to do that because whenever we get the answer, whenever we go check to see if this is exact, it's actually going to turn out to be exact, which means we can use that method to solve the differential equation, which is actually pretty cool. So if I dy this guy, I get 4xy. And if I ddx the second guy, I get 4xy. Yay! So that means I can actually solve it. So let's go ahead and practice solving this just for fun. Because it's good practice, that's why. So I've got that dx is going to be equal to 3x squared plus 2xy squared, or that df dy is going to be equal to 2x squared y. It's not really or, they're both true. It's just a question of which one do I want to use. Now because I'm inordinately lazy, I'm going to use the shorter one. So I'm going to use that partial f is equal to 2x squared y partial y. As I integrate both sides, on the left I get f, on the right I get some other number, x squared y squared, plus a function of x. Since I was integrating with respect to y, that means I'm left with a function of x. Now I have to use the other guy to finish this off. I know that the ddx of the f that I found, x squared y squared plus h of x, I know that the ddx of the f that I found is equal to, has to be equal to 3x squared plus 2xy squared, because that's how I solved this exact equation. That's how I came up with all this theory to begin with. Well, I didn't come up with it, somebody came up with it. Plus h prime of x is equal to 3x squared, like this. And as I get this to go through, I can go ahead and I can subtract stuff out. H prime of x is equal to 3x squared, which means that h of x is equal to x cubed plus c. Therefore, f, the solution, is x squared y squared plus x cubed plus c equals 0. And I was able to find a solution to that nonlinear, totally weird, inexact differential equation. Kind of? Okay, one more. This is a good practice. This is one where you should definitely pause the video and try to work it out on your own. This problem here should look pretty familiar. We actually solved this in a previous video when we were talking about nonlinear methods. And at this point we just guessed. So last time we solved this problem, we guessed a solution that looked like this. And we went through and we found it. It was amazing. But the question off the top was, well, how would you guess that? and I have no idea. But if you can't guess, then you can try using the exact method. So the first thing you want to do on this problem is you want to rearrange it so it meets our strategy, or meets our kind of template of m dx plus n dy equals 0. And then from there, prove that it's not exact, then figure out the integrating factor and make sure that the integrating factor makes it exact, and then take it from there. So pause the video, and then if you get stuck, then just watch the video to the point that you got stuck, and then try going again. So pause the video, see how far you can get. And we'll assume that that happened. Okay, so I've got 3x squared dy dx equals y cubed plus x. 3xy squared dy equals y cubed plus x dx. How am I doing partials now? I've just got partials on the brain. dy dx dx. It's getting late. I'm getting tired. You have no idea what that's like, right? That's why you're probably watching this video at 3 in the morning, because you have no idea what it's like to be tired. I'm always going to keep things in the order of x and y just because I'm a visual learner, kind of. I'm a pattern matcher, so I get used to certain patterns, and I like to see that at m coming first. Now, if you were able to get this far, great. Just kind of spot check your solution and then keep going. If you made a mistake, just fix the mistake and then try to go from there. I'm going to assume you're doing the best thing that you need to do for your own education. So I'm going to dy this, and I'll get that. And I'm going to ddx this, and I'm going to get this, which is stupid because it's so stupid close. I can't even write. I'm so angry because I shouldn't have to do any extra work, and now I'm going to have to work, and working isn't fair because, stuff. So I'm going to try my minus ny over n. So I have minus 3y squared over n. Ooh, yay! Minus 2 over x. All x's. Yay! So since it's all x's, that means that I'm going to multiply the whole thing by this thingy. So that's 2 ln e to the 2 ln x, negative 2 ln x, which is e to the ln x to the negative 2, which is x to the negative 2, which is 1 over x squared. So I'm going to multiply the entire equation by 1 over x squared. So I've got 1 over x squared times this whole thing. I'm just going to go ahead and write it out. But I'm going to multiply this whole thing up here times 1 over x squared. Okay, so I've got plus, just want this, 3y squared over x. Okay, just looks funny. Okay, and I think I did that right. I lost my paper again. This keeps happening. Right. Okay, so my next check is I want to make sure that the dy of this thing which is minus 3x squared y squared, and that's 0. This, I hope, equals the ddx of the second one. And 3y squared times x to the negative 1. That's negative 1 goes out front, y squared x to the negative 2. Yay! They're exact. That means I can actually solve this. So that means that partials. So again, if you got this far, pat yourself on the back and see how well you did. If you made some mistakes along the way, then go, fix them and stuff. And then see how far you can get. So I have to pick one of these. I already know which one I'm going to pick. I'm clearly picking the first one. Just kidding. I'm clearly picking the second one, because the second one looks easier to deal with. So I've got df is equal to 3 over x times y squared dy. And if I integrate both sides, I've got f is equal to 1 over x times y cubed plus some random function of x, because I'm integrating with respect to y, so I should get some function of x. Okay? Then I'm going to, oops, not cross that out. Then I'm going to use this guy here. I know that I ddx f, which is 1 over x, this thing. If I ddx this thingy, then I should end up with minus y cubed over x squared minus 1 over x. So I'm going to perform the differentiation. I'm going to rewrite this as x to the minus 1 just because it's easier to differentiate that way. So pull the minus 1 out front. It becomes x to the minus 2 plus h prime of x. And that somehow has to equal this. And luckily these go away. That's just kind of nice. So I've got that h prime of x is equal to negative 1 over x. So that means that h of x is equal to negative ln of x plus c. So what's nice about that is now I can create my f function, which is 1 over x y cubed plus h of x, which is minus ln of x plus c. And that equals 0. And therefore I was able to find the solution to this lovely first order nonlinear partial differential equation, ordinary differential equation, and take it from there. So I hope you got something out of this. Hope you had fun.